Hello, welcome back, and in this video we will try to teach you how to do the electronic configuration of a certain element or an ion. Now generally you have to remember that electronic configuration is just the distribution of your electrons in an atom or in a molecule based on where they are found in these orbitals, right? So orbitals are generally the places where you can possibly find your electrons, and later on you would know that it can help you determine the shape of your atoms or molecules, but the focus of this video will only be on the electronic configuration. Alright, so we have to know first, by looking at our periodic table, that there are some important facts that we can or that we need for us to determine the electronic configuration of a certain element or an atom or in a molecule. Alright, so we have here the periodic table, which is very important in doing the electronic configuration. We must know that these are here your elements grouped together with the similarities of their properties in a column or in a row. Alright, so this has following numbers. Alright, and I have written now the major group numbers. Now when you say group, that's from top to bottom. Now when you say a period, you go from left to right. Alright, so as well, the periods here are also numbered from 1, 2, 3, 4, 5, 6, 7. Let me show you that as well. Alright, so we have now the period numbers. Period 1 here, period 2, and so on. Okay, now the group numbers 1, 2, 3, 4, 5, 6, 7. Now these are the major group numbers. We also have some group numbers here, but mostly this will require some exemptions to the rule. So we must focus first on the general rules before we go to the exemptions. Now, in doing the electronic configuration using a periodic table, you have to remember that this here corresponds to some orbitals. Now, what are your orbitals? Let's look at your orbitals. Okay, so these are the different blocks corresponding to the orbitals looking in your periodic table. So you have the S block here, we have the P block over here, the D block, and the F block here. So this tells us where in your periodic table will you be able to find elements or atoms that has their valence electrons on this specific orbitals. Okay. Now what are valence electrons? Valence electrons are just the electrons that do the work in the bonding part when there is a reaction. Okay, so in terms of the energy level, it's also important because when you try to fill up the electrons for us to determine the electronic configuration, we have to know which has a greater energy level. So we have to look at how the electrons are being filled up in this S, P, D, and F orbital. So let's look at that. Alright, so I have here two diagrams that will help us determine and how do we fill up the electrons based on the energy level. So the N here represents the period number. Okay, so 1, 2, 3, 4, 5, 6, 7. Then we have here the S orbital. As you can see, S, P, D, and F. So generally, as you go from left to right, that means lower energy to a higher energy level. But when you try to have a more number of shells represented by your N number here, the energy level also increases as well. So you start from your 1s, then you have your 2s. As you can see, the arrow is being or there is a diagonal arrow representing to the direction of where the next orbital will be filled in. So you have 1s, then you have 2s. After 2s you have 2p, 3s. After that you have 3p, 4s. Then you go back to 3d. Now why is that? Because when you look at your blocking here, right? So the D block here is usually n minus 1. Alright, n again is your period number. That is the principal quantum number, and it tells you the number of shells in your orbital, sorry, in your atom or in your molecule. Okay, so n minus 1, so that's why we have 3d here. Alright, then 4p, back to 4p, then we go to 5s, and you simply continue that until you go here. You only limited our diagram here because these are the only so far in the periodic table that can be accommodated. Alright, now if you look on this diagram on the other side, as you can see, this will help us more visual in terms of the orbital diagram. The box here represents the orbital diagrams with their corresponding energy levels. So you have again 1s, then followed by 2s, then 2p. As you can see here, then 3s over here, then 3p, then we have 3d and 4s, and so on. As you can see, one box represents for 1s, 2p has 3 boxes. Now one box represents an orbital. An orbital can only accommodate 2 electrons. So one box can accommodate 2 electrons. So you have 3 boxes for the p orbital, it means 6 electrons. 5 boxes for the d orbital, that means 10, total of 10 electrons. Then we have here 7 boxes for the f orbital, which means we can accommodate 14 electrons. So that's 2, 6, 10, 14. S, P, D, and F. Alright? So this will be our guide for us to know the electronic configuration of our given elements or ions. So let's do one example. Alright, so let's look at how do we determine the electronic configuration of beryllium. So the first step is for you to look at the periodic table and determine how many electrons does your beryllium has. So let's do that. Okay, so we're here, beryllium Be is element number 4. Now the numbers here again are your atomic numbers, and it tells you the number of electrons that a certain atom has. So it has 4 electrons. So it means we have to distribute 4 electrons using the energy orbitals that we have seen earlier. So let's do that. Alright, so as I have told you, we start with the lowest energy orbital, and that is the 1s. And as I've shown you earlier, one box can accommodate 2 electrons. So one box can accommodate 2, so that's 1 electron here. Then another with the opposite spin. So that's 4 minus 2 electrons, we only have 2 more electrons left. So we go to the next, which is the 2s electron. Now as you can see here, the 2s has only 1 box. So it means it can only accommodate 2 valence electrons as well. So we'll write here the 3rd, then the 4th. So we have now used up all the 4 electrons of your beryllium. So that tells us that the electronic configuration will be 1s2 and 2s2. So let's write that down. Okay, so we now have written our electronic configuration. We have 1s2 and 2s2. Now you must be wondering, why is it on the exponent? It's not the mathematical exponential form, but this is the notation of your electronic configuration. The number here represents the number of shells. So they have the first and the second shell, then the letter of course corresponds, SPDF corresponds to your subshells, and the superscript here corresponds to the number of electrons in that certain subshell. Alright, so that means we have 1s2 containing 1s with 2 electrons, and you have the 2s subshell with 2 electrons as well. 2 plus 2 corresponds to the total of 4 electrons for your beryllium. Now earlier we mentioned about valence electrons. Now this will actually look at the electrons in the outermost shell. So if we go back to our diagram earlier, we have used up 1s and 2s here. So the outermost electrons usually would be of course in the outer shell, which is on the second shell. So the number of valence electrons for beryllium will only be 2. Then if you go back to the periodic table, here, group 1, group 2, which you can see beryllium. So group 2, all of these elements here will have 2 valence electrons. So that will tell you that the highest energy occupied orbital corresponds to the group number, or to the number in your row. That's from top to bottom. To your column rather, from top to bottom. Alright? Now, we try to correct our answer. Not correct, but compare it with our Wikipedia answer. So let's check that. Alright, so this is the page on Wikipedia, and we look at the electronic configuration of beryllium. We have here helium in a open close bracket and 2s2. Now our answer earlier was 1s2 and 2s2. Now you must be wondering why helium is placed here. Now this is a different way of writing your electronic configuration, and this is called as your core electron configuration, because we are using the notation of our group 8 elements, or your noble gases, because they're considered to be highly stable, and their core configuration actually is represented by this. Okay, So what is helium is actually, if you look back at our periodic table, helium is here. It's element number 2, so it has 2 valence electrons. So we have 1s2, sorry, 1s, then we have 2s here. Okay, no, sorry, 1s2. So that's one here and another here. So every box actually corresponds to a single electron if you try to use it in a simple way. Alright? So helium to s2 is your beryllium, or 1s2, 2s2, and that is your beryllium. So that's all for this video. I hope you've learned something. Thank you for listening and continue learning.